So I guess I can get started. Welcome to my talk, Designing Data Intensive Applications on Relational Databases for Maintainability. My name is Simi Oluwatomi, and thank you for joining me. I am a backend software developer. I like playing chess and table tennis. I also love trying out new things. I have um, I have played around with microwave transmission, climbing masts, climbing telecoms masts. I have shot some weddings for some of my close friends. I have done some graphic design, a little Android development, and some cloud computing. So that is about me. Currently, I am a tech lead at Brass Technologies. Every day I go to work, many times I feel like an imposter, but I've not been fired yet. So I guess I am doing a good job. Now, about you, those who are watching, this talk is for people who don't hate SQL. Basically, if you are watching me, it means that you have built applications on relational databases or maintaining applications on relational databases or planning to build applications on relational databases. Essentially, it means that you use relational databases. Now, to my table of contents, we are going to be talking about SQL data types, SQL keys, database design, and database transactions. Many of the challenges that I have, many of the mistakes that I have made, that I have seen other people make, and that I have inherited from other people are usually within these four domains around database design. And hopefully, by the end of this session, we should be able to clarify some of these things. So to start with, let us talk about SQL data types. Basically, SQL says that if you want to store a data in a column in a database, you should specify what kind of data that is upfront. Now, it doesn't mean you can't change from one data type to another. You can. But at every point in time throughout the lifetime of the data, it must have a type. And when inserting or updating that type, the database will always maintain integrity of the data type that you specified. So we have strings, we have numerics, we have date and times, we have binaries, and then I have a section for miscellaneous data types. The miscellaneous data types are data types that are available depending on the relational database vendor. So for instance, Postgres allows you to store spatial data, that is data regarding a location. MySQL also does that, but you have to install an extension. Postgres stores XML data, MS SQL, Postgres, Oracle, they all store JSON data. Some store Booleans. So different types of data are available for you to choose from when declaring what type of data you are going to be storing in that column. Now, you may be wondering, why do we need to talk about data types? Number one is that by selecting the right data type, we can optimize data storage. I was watching one of the talks earlier, and the speaker mentioned that uh, data is not immediately written to disk, but at the end of the day, that data ends up in the disk. So the data that you have in your database is just like the files that you store in your computer. So the question is, are you using the right data type? If, because at the end of the day, you want to make sure you are not using too much storage or too little storage. For instance, if you want to store Nubank bank account numbers, which are always 10 digits, then it doesn't make sense storing them in a column that is stored as 2 gigabytes on disk. So that is one benefit. The second benefit is data accuracy. Very early in my career, I dealt with something that I hope nobody ever does. I was working with a BVN API. We did the integration and then we went to sleep. The next day, the product manager says, users are complaining that their date of birth is wrong. So it felt weird. It ended up being that the BVN API was sending the date of birth of people, but the year was 2 digits. So instead of having a year like 1979, you only had 79. Now, when you try to pass 2 digit years in most programming languages, because the Unix timestamp starts January 1st, 1970, any 2 digits before 79 gets interpreted as being in the next century. So someone that was born in 1960, for instance, because the date time library was seeing only 60, it will tell us that person was born in 2060. So we had to build workarounds to correct that kind of behavior. Now, imagine if the data was stored accurately using the correct data type. We wouldn't need to do that kind of work. Now, imagine many developers that rely on the data coming from that API. We all would waste hours fixing that bug when it could have just been fixed by storing that data in the right kind of format that it should have been in the first place. The last two things here is query readability and query performance. As developers, we talk about naming things. We talk about naming functions, naming classes, naming variables, but we rarely talk about the readability of our SQL queries. It is not that SQL is bad, it is that many times developers write bad SQL queries. So in the end, the person reading it doesn't understand what that query is trying to do, especially if you're not using like an ORM, an object relational mapper. So improving query readability starts by storing data in the right data types. Now, the consequence is that our queries would be faster because the query is readable, you write it better, so the database would execute those queries in a faster manner. Imagine that you want to select a bunch of things from the database, and before you do that, you do a join first. Meanwhile, you never needed the join in the first place. So your database would not do extra work to do what it wants to do or to give you the data that you require from it. Let us move on. Now, a word of caution. Just because a data type exists does not mean that you must use it. Now, this is a mistake that I have seen many developers make. I have made some myself. So for instance, if a user uploads a file, and because your database supports you storing blobs, you do a base64 encoding of the contents of that file, and you stick it inside your blob and save it in the database. Eventually, a user is going to wake up one day and upload an image of 100 megabytes because camera phones are now improving their resolutions. And then just one row in your database would occupy over 100 megabytes when it is saved on disk. So because the blob storage type is there does not mean you must use it. Because all these data types are there does not mean that you must use it. You should know what to use per time. You should know when to use what and the trade-offs that are involved. Now, let us talk about SQL keys generally. And the first thing is that we must identify or define what a key is. So what is a key? A key is an attribute or many attributes that allow you to identify a row uniquely in a database. Note it must be able to identify every row by uniqueness. So what are the key types that we have? I'm sure you'll be shocked at. So, okay, before we go into that, why do we need keys? Number one is that they enforce data integrity. Number two is that they allow each record in a table to be uniquely identified. And then number three is that they establish relationships between tables. Now, let us take a family, a father, a mother, and a child. To identify everyone in that family, we only need to run a test on their DNA. So we can say that a DNA or the DNA of an human being is a key that uniquely identifies every human being. Now, to establish, so if the father wakes up tomorrow and says, this daughter, my daughter does not look like me, she looks like my grandfather instead, or she looks like the uncle of the grandfather of her mother. The way to establish the relationship between the father, the mother, and the child is simply to run a DNA test. The DNA test with a very large degree of accuracy would establish that relationship. So again, you can see that even in the human body, we have keys, right? Then the third analogy is that everybody has a unique DNA. Everybody. The baby that is going to be born in the next 5 minutes has a unique DNA. The person that will be born in China in the next 1 hour has a unique DNA. So we need these things in our relational databases so that our data remains that our data still retains its integrity so that we can identify every row and so that we can establish relationships. Now, types of keys. Some people may be shocked by some of the things they are seeing on the screen right now. Number one is that we have a super key and then we have a candidate key. Remember that we have said that a key allows you to identify every row uniquely in a database. So what is the difference between a super key and a candidate key? The only difference is that your candidate key cannot be null. In any universe, in any planet, your candidate key cannot be null. Meanwhile, your super key can be null. There are other differences, but this is the biggest difference. Now, let me go back to human beings, right? I have talked about DNAs, but there's another key for every human being, and that is a fingerprint, right? For the duration of the life of a person, their fingerprint is unique to them. Even twins don't share the same fingerprint, as we have been told by biology. But what happens to a person's fingerprints when they die and their body decays? Eventually, that fingerprint is nowhere to be found. So we can say that the fingerprint becomes null after some time. But the DNA, according to science, can still be preserved for hundreds, if not thousands of years. So in this case, we can say that both the DNA and the fingerprints are super keys, but only the DNA is a candidate key because the fingerprint can become null at some point in time. I hope you are following. Now, let us talk about other keys that we have on the screen. We have the primary key. Now, the primary key is simply the key that you chose to be your number one. That's the simplest explanation that I can give to it. Your secondary key could have been the primary key. Maybe if you liked the name better, it could have been the primary key, but it is not. It is also a key, it is unique. It could be a candidate key that in that it cannot be null in your system. But because you just didn't like it, you decided to make something else the primary key. Then we have a compound key. A compound key is a key that relies on multiple attributes to enforce its uniqueness. So in the case of the family, the uniqueness, the DNA of the child depends on the uniqueness of the father and the mother's DNA. So combined together, we can say the father's DNA and the mother's DNA are the compound keys of a child. Now, what is a foreign key? A foreign key is simply your primary key in another database table. Simple. So I hope that I have been able to explain the keys and that we are following along. Now, let us look at this sample table. And it is just for an example. We see that we have an ID that is a primary key, and then we also have a UUID. But our UUID is not the primary key because we don't like it. And then we have a type ID that is a foreign key in a types table. And then we have the name, the number, the reference, and the vendor. I love Game of Thrones, so please permit me. Now, if you work with fintech APIs, you will realize that when you want to provision an account, for instance, with StackPay or with Flutter, they would ask you to generate a reference. And that reference is going to be unique to their systems. But in your system, you may not want two accounts to have the same reference, right? So we could say that our reference is also a secondary key. Now, going by logic, a bank should not have two account numbers that are the same, right? So Iron Bank and Iron Bank should not issue two account numbers that are the same. StackPay should not issue two account numbers that are the same, and the same for Flutter Bank. Now, but because we are using multiple vendors in our system, we cannot completely say that the number is unique across the database. So in this case, we could say for the combination of the number and the vendor, they must be unique. So in that case, our number column and the vendor column then becomes a composite key. I hope this example illustrates the different kind of keys that we can have in a database. Now, what are the trade-offs to selecting a primary key? You don't select the primary key because you like its name. You don't. In as much as I may have given that as an example, that is the wrongest criteria to use, right? And you don't select a secondary key because it is short or because it has bad character. No. These are the trade-offs that you really need to consider. The first is your insertion speeds. How fast do you want to be able to create new rows in your database? That is all. So if you read it, you see that your auto increment key or your serial column is faster than a ULID or a GUID. That is also faster than a UUID. Now, the speed of all of this, so let's assume that in this case, your auto incrementing column is using Bolt, and then your ULID is Tyson Gay, and then your UUID is Ashafa Powell, right? For people who love track and fields, you should be able to understand what I just said. Now, these conditions are sometimes dependent, insertion speed is sometimes dependent on the database engine and the database vendor. So for instance, on MySQL using the InnoDB engine, UUID is extremely random. So when you insert it, it is slow. But in a database like MS SQL, the same condition may not apply. The second consideration is disk space. So how much disk space do you want to use to store your primary keys? Don't forget, your primary keys at some point will become foreign keys in another table. So your auto incrementing column would only be stored using 8 bytes, just 8 bytes, nothing more, nothing less. On your table, 8 bytes. On the foreign key, also 8 bytes. Your ULID column will be stored using 12 bytes. Meanwhile, your UUID column will be stored using 16 bytes. The byte looks small, but please let me remind you that 1 byte eventually, by the time you multiply it, becomes a megabyte. And then when it becomes plenty, it becomes a gigabyte, and so on and so forth. Now, the third trade-off is randomness. If you're building a distributed system, you want your keys to be random. You don't want any chance of collision because your distributed systems should enforce uniqueness. So in that case, your UUID and your ULID are better than your auto increment or serial columns. That's just the truth. Because your auto increment serial or serial columns in a distributed system would also be replicated in another database, in another server, in another region. So these are some of the what I think are the most important trade-offs that you need to consider. Don't just wake up and say, oh, I want a UUID. No. Identify the trade-offs. Don't just wake up and say, oh, they told me that it is ULID that is a new thing. No. Identify the trade-offs. Now let us talk about database design. The most important thing about database design are relationships and normalization. Every other thing about database design is secondary to these two principles. So let us look at relationships. In a system that manages the computers assigned to employees, an employee can only have one computer at a time. If you have seen a company that assigns 2 computers to one employee at the same time, please send me their name. I may want to talk to their HR, maybe they can also send to me. A post is going to have many comments. So this is a one-to-many relationship. Then a book can have many authors, and many authors can write a book. So in the first 2 relationships that we have been looking at, the relationship exists only between 2 tables. But in this relationship, the relationship exists between 3 tables. So we introduce an intermediate table to manage the relationship between those 2 other tables. Then the last relationship I want you to look at is a self-referencing relationship. That is a table that has a foreign key, and that foreign key leads to itself. So in your e-commerce website, you have a category. Under that category, you have subcategories. And then under subcategories, you have subcategories, and so on and so forth. While you could store those data in different tables and reference them, when you look at the shape of your data, you would see that they are all categories. So the best way to store that form of relationship is to use a self-referencing relationship, such a way that once something has a parent, then that means it is a subcategory to something else. So these are the relationships I want you to be on the lookout for. Every other database relationship that you come across in your programming language, maybe or in the ORM you use, is a form of these relationships. Now, the quick advice I need to give: your foreign keys are best managed by your relational database management system. Don't be afraid. Foreign keys were not invited to bite you or to kill you. I know you have to create the foreign table first before creating the table that links to it second. Yes, that constraint is there so that you don't kill yourself. Stop managing your foreign keys only in application code. it's not good. Now, when we talk about normalization, there are like 8 normalization principles, but I briefly want us to look at just 3. And the first is the first normal form. And it says that every column of a table should contain only atomic values, and that there should be no repeating groups of data. So if you look at the table, we have the first name, last name, and then the phone column. But you see that the phone column holds 2 phone numbers. And because of that, it is breaking the first normal form. By fixing that to repeat the row where the phone number is different, or having a primary phone or a secondary phone, we make the data to be in first normal form. The second normalization principle is the second normal form. And for you to consider the second normal form, you must first be in the first normal form. Now, the second normal form is only pertaining to tables that only have composite keys. I made us look at composite keys earlier. So that means that there is no primary key, only composite keys, right? Now, what happens is that we usually make the assumption that this data, I don't want it to store in that old table. Let me just put it in this new table. No. If that data depends on only one member of that composite key, then it should be in the table of that member. So what this means is that teacher is not supposed to be on this column. Why? Because the teacher teaches a subject. Where should it be? It should be on the subject table, such that we can get the teacher of a subject just using the relationship. So this makes the data be in the second normal form. Now, the third normal form is that you must be in the second normal form and that you avoid repetition. Now, this repetition is so as to guard against integrity when you are updating your database tables. So look at this table. We have the state and we have the country. Meanwhile, the better way to store this data is to extract the state to its own table and then extract the country to its own table. This way, the data becomes in the third normal form. There are other normal forms, but by the time you go through the first normal form, the second normal form, and the third normal form, believe me, your database will go very far. As they say on the streets, oh my lord, far. Now, let us talk about database transactions, right? Transactions are meant to ensure the ACID principles of a database, right? And those are atomicity, consistency, isolation, and durability. The problem is that you are building an high traffic application, you write your SQL queries or your database query, you throw them behind a database transaction, you go to sleep, and then you wake up tomorrow and discover that somebody has sent money, somebody sent 13,000 4 times when they had only 13,000 in their account balance. So you start wondering what went wrong. I used a database transaction. This thing is not supposed to happen. The problem is that SQL happened to you, not that user. SQL happened to you. So let us look at how you can ensure that database transactions work for you. The first is that you must use schema constraints that follow business rules. Schema constraints that follow business rules. One of the principles you could use is to say, oh, my account balance column must not be less than 0. So that is a key schema constraint. Immediately, even when you try to update that account balance column to minus 13,000, the database engine or the database software is going to tell you, oh, Baba, I know if you do it. The second principle is to use database logs. Now, we hear about logs, right? So what are logs? We have 2 types. We have the exclusive log, and then we have the shared lock. What is the difference between the two of them? They are both locks, but the way they operate is different. For a shared lock, many processes can read that resource at any point in time. Many processes, underline that keyword, many. The difference is that none of them would be able to perform an update until that lock is released. Many can retrieve the resource, but none of them can update until the lock is released. That is for your shared lock. For your exclusive lock, only one can retrieve and update. Only one can retrieve it. Once it acquires that exclusive lock, any other process that wants that lock has to be on a queue. Once it is done with the lock, it will release it to the next process. And that next process will release it to the next process, and so on and so forth. So what are the issues that happen? Number one, we have lock contentions. So your exclusive lock, for instance, this database is fighting for this lock. That transaction is fighting for that lock. The two of them are fighting for the same biscuits. If you look at children, all of them are fighting for the same biscuit. You are not supposed to do that. No, there are ways to do it. The second issue are deadlocks. Deadlocks happen when a transaction has obtains a lock on a resource, and then without releasing that lock, tries to obtain another lock on another resource. Now, if a separate process has a lock on that first resource, because the first process cannot acquire that lock, the two of them will now be fighting a deadlock. So what is going to happen? How do you solve these issues? For your lock contentions, you can actually tell your SQL engine what to do. Baba, select this account number that has this value. If you cannot get the lock, don't what? Don't wait. Just go. If you cannot get the lock, don't wait. So instead of being on the queue, just be coming back home. The second one, you say, please run this database query. But after you find this account number, if it is locked, do what? Skip it. You get, just leave it, just they go. So these are the ways that you can deal with lock contentions. Believe me, these queries are written in MySQL, but the same applies to every database engine that you can think of, right? Now, how do you manage deadlocks? So we have done lock contentions. How do you manage deadlocks? Number one, use logs for write operations only. If the only thing you need to do is to display the account balance of this account, why are you fighting for a lock? What are you doing? Number two, when you want to acquire a lock, use your database indexes. So your indexes are like your keys, like your super key, your candidate key, your primary key. Use those so that you are not selecting a large number of rows, right? You want to select something, just one. So write your SQL queries to lock only that attribute. Number three is that you should keep your transactions small. Many times you want to do 100 things inside one transactions. Abba, what is your problem? Keep the transaction small. Do 2 or 3 things. Commit the transaction. When you commit the transaction, come back for another lock. Then number 4, remember that your logs are stored in your database memory. Don't forget, your data is first stored in memory before being flushed to disk. But the logs you are obtaining on those data is stored in your memory, in the database memory, in the RAM. So if you are not careful, by the time you are carrying logs up and about, You are locking everything, locking everything, locking everything. The RAM of your database is going to be used up. It is going to be used up. Once the RAM is used up, instead of locking the rows, your database will now lock the table itself. And once it locks the table, wahala ti ṣẹlẹ̀. Like everything has come to a standstill. You get? So if you follow these principles, the chances that you are going to end up in a situation of deadlocks is going to become small. There are more, but I don't want to go into some things that are like extremely technical. Now, the last one are mutexes, right? Now, mutexes are in application code. There is no mutex in MySQL. There is no mutex in Postgres. The mutex is in your application code. So you acquire the mutex that performs like a lock. So instead of doing like your shared lock or your exclusive lock, you are not doing those. You are only acquiring a mutex lock that is outside your database. You perform the database operations, you commit those database operations, then you release that mutex lock. Now, what is the difference? Your mutex, you can implement it using something like Redis. I have done that several times. I have seen some people use, I think, RabbitMQ for a mutex, or I think Memcache, right? So your mutexes are outside the database and they can work for you. Now, when talking about transactions, you can combine multiple strategies. You can employ a mutex and a database lock at the same time. Nobody is going to beat you for it. So you can combine multiple strategies depending on your use case. If you are not using Redis and Memcached in your system, using a mutex is almost impossible for you. Why? That is your use case, right? So identify your use case, identify your own cloud infrastructure or your application infrastructure, then combine these strategies to mitigate these risk conditions. Thank you very much. Once again, my name is Simi Oluwatomi. You can find me on Instagram, Twitter, and LinkedIn using just my name, Simi Oluwatomi. Let me know if there are any questions. Okay.
Section analogies. Someone says, Andrew says, you mentioned self-referencing table relationships. Can you give an example of this? I didn't quite get this.
Okay. So in many financial applications, we have accounts, right? Now, an account, you could want to implement a sub account feature, right? An account that is tied to a parent. So let's say that you have a bank account and you want your child to be using the same bank account, but you want to limit how much they can spend in a day. The way people install their profile on their Android phone and then give to their children and implement children constraints, right? Now, that sub account could be a sub account table that references its parent on the account table, right? But you could also decide that why not put the sub account and the account together, right? So that is one analogy. Let me go back to the categories analogy. So on your Jumia shopping website, for example, you have clothes, right? Now, under clothes, you have men's clothes, women's clothes, and children's clothes, right? Now, when you click on men's clothes, under men's clothes, you are going to see shirts, trousers, belts, and so on and so forth, right? Now, when you look at all these categories, you see that the only thing that they have is a name, right? The clothes, the men's clothes is a name, the clothes itself is a name, the shirt is a name, the jeans is a name, the trousers is a name, right? So your subcategory could have a parent ID on it that links to its parents, right? The SQL query, if you have not written that kind of thing before, may seem strange to you because I mean relationships should be between multiple tables, right? But no, you can have that in that format and in that shape. I hope I was able to answer your question.
Yeah, just me. I'm just curious. Just like the examples you gave with the clothes, does that mean like the two tables, their rows like are in the same, basically just referencing an ID in the same table?
Yeah,
Is that the gist? Okay, okay,
yes,
thanks.
that's the gist. So it's going to have the name, it's going to have its ID, but the parent ID would so
Would be
for
an
your
ID on the same table.
yes
Okay, okay.
on the
I
same
think
table. So if you enforce that constraint, the foreign key constraint in your database software, and you click on that ID, it would take you back to the same table,
okay.
right?
Okay. Next one, Eden says, what's your take?
On ORMs, right?
Yeah.
I use ORMs. ORMs are good, right?
Mhm.
But um, you need to go below the surface layer, right? How does your ORM do things, right? Some would say ORMs are slow for some specific types of queries based
Application.
on how they write, based on the SQL that the ORM produces for that query. So, for instance, in Laravel, you have a where relation method on your eloquent stuff. When you look at the query produced by that method, you would realize that it can be slower than using a normal join. So ORMs are good. They allow you to think about databases like programming languages. But their limitations are in that if you don't understand how they work under the hood, you may shoot yourself in the foot.
Okay, thank you so much. I think that's the last question we have, and we are over time. Games. This is the last session. Thank you so much. It was really informative. Thank you, Simi. You can connect with him online. He has his username on display. So thank you.
Thank you. Thank you guys for joining. I had a wonderful time. Hope you too had a wonderful time. Bye.
Bye.